Okay. The next concept that we're going to look at that's somewhat related to norms is spectral radius of a matrix. Okay. We'll come across this concept again later towards the end of this segment again. The spectral radius of a matrix. So given any matrix A, so any square matrix A. Okay. I'll explain why. So spectral, whenever you see the word spectral, it usually has something to do with eigenvalues or singular values. Okay, that's when you put that adjective, right? When you see the word radius, well, that has something to do with how far from the center you can go or something like that, right? So if A is a square matrix, the spectral radius is simply defined as the eigenvalue of the largest absolute value, okay, of the eigenvalue. So that's going to be max of lambda I. Okay, I equal to 1 to n. So basically, you take all the absolute values of the eigenvalues of A and you pick the largest among them. Okay, the largest absolute value. Okay, lambda I of A. So it's as if you take the eigenvalues in a vector and take its infinity norm, right? That's what a spectral radius of a matrix is, right? So first thing to remember here is that A, I said, is square. It's not necessarily symmetric. It can be any square matrix, right? So not necessarily a symmetric square matrix, right? Any square matrix you can define the spectral radius. Okay. Now if you take an arbitrary matrix that's not symmetric, your eigenvalues can be complex. Okay, they don't have to be real. Right? Symmetric matrix has real eigenvalues, but other matrices can have. In general, you will get the characteristic polynomial, right? Det of lambda I minus equal to 0. The polynomial can have complex roots. If your matrix is symmetric, it will not have complex roots. It will only have real roots, I mean. But in general, it could have complex roots if A is not symmetric. Okay. So the radius refers to the radius in the complex plane, that is, right? So let's say you imagine the complex plane, meaning that you have the real part of this is the real axis and this is the imaginary axis. And let's say these are all your eigenvalues of A, right? So some of the eigenvalues may be in the real line, many of them are not, right? Most of them have a real part and imaginary part, right? What you are looking at is the eigenvalue that has the largest magnitude, meaning that the complex number that is furthest from the origin in the complex plane. And the eigenvalue that is farthest from the origin in the complex plane. That here in this representative picture would probably be this one, right? So in some sense, this is the thing that you are looking for, right? So this is called the spectral radius. Okay, so this is called the spectral radius. That's why the term radius is common here, meaning that you are looking at the circle in the complex plane within which all of your eigenvalues will lie. Okay, it's defined for any matrix. Okay, any arbitrary square matrix, you can define the spectral radius. Okay, the spectral radius is important because it has, I'll tell you in a minute. We'll look at one of the main consequences of having spectral radius, of the spectral radius of a matrix. I hope this is clear what this means. Okay, the spectral radius is not a norm. Right? For example, you can have a matrix that has 0 spectral radius. For example, let's take a triangular matrix, a 2 cross 2 triangular matrix with 0 on the diagonals and 1 in the upper diagonal, something like this. This is a matrix that is upper triangular, 0 on the diagonals and 1. And this matrix is not a 0 matrix, right? It's definitely non-zero matrix. But what are its eigenvalues? What are its eigenvalues? Right? Does everybody know that the eigenvalues are 0 and 0? Because if you try to find its characteristic polynomial, you will simply get lambda square. Okay, lambda square will be the characteristic polynomial of this, right? And that has root 0. So the eigenvalues are simply 0, right? We simply say 0 is an eigenvalue of this matrix, right? So what is the spectral radius? Is 0, right? So even though this matrix is not 0, its spectral radius is 0. That never happens for norms, right? If you have a norm, right? Any norm, doesn't matter what norm it is, you take this matrix, it will be non-zero, right? For example, the Frobenius norm of this matrix is 1, right? For those of you curious, please try to find out what is the spectral norm of this matrix. Okay. By finding its singular values, right? By the way, this matrix will is actually a very useful matrix for many examples, especially when you are dealing with non-diagonal, anything that's non-symmetric, not diagonal, in non-symmetric matrix, right? This is one of the first examples you should think of for a non-symmetric matrix, right? There is a reason for that. This matrix is like very fundamental non-symmetric matrix. Okay, we'll come back to this later when we do Jordan blocks. Okay, we'll do that later. Right. So this matrix has spectral radius 0, but it doesn't have norm 0. In fact, you can find out its Frobenius norm and spectral norm. You see that they'll be non-zero. Okay, fine. So it's definitely not a norm, right? But what is very interesting here is that for any norm, induced norm, rho of A will be less than or equal to the induced norm. Okay. Okay. So the spectral radius of a matrix will always be less than or equal to the norm of a matrix. Okay. So in some sense, the norm serves as an upper bound on the spectral radius. Okay. Okay. How do we get this? You actually get this just from the definition, right? So remember what is norm of Ax? Okay, by norm of x, right? This is basically norm of A. Okay, so norm of A, the induced norm is defined as the largest value of the gain. This is the gain, right? So we can say it like this, right? It's greater than or equal to norm of Ax by norm of x. Correct. Now, if you take x to be like an eigenvector of this matrix, right? This inequality works for all x, right? So I can just pick x to be an eigenvector of the matrix. In that case, I'll get norm of A bigger than or equal to norm of Ax, which is going to be equal to lambda x. Lambda, if x is an eigenvector corresponding to lambda, then it's going to be like this, which is equal to the absolute value. Okay. So norm of A, any induced norm, okay, it doesn't matter, by the way. It can be any induced norm. It's not just the spectral norm, right? Any induced norm is greater than or equal to the largest, is greater than or equal to any eigenvalue, absolute value of any eigenvalue of the matrix, right? You would have picked any lambda here, right? So the norm of a matrix is bigger than or equal to lambda, and hence the norm of a matrix is bigger than or equal to the largest eigenvalue as well. Okay. So the norm of a matrix is bigger than or equal to the spectral radius. Okay. Right. We came across this concept of spectral radius earlier when we did the power method, right? If you remember, the main idea behind the power method was to find the eigenvalue that has the largest absolute value. Okay, in that I'd also used this word then in that lecture, if I remember correctly, and we were trying to find the spectral radius by taking powers of the matrix. Okay, that in fact is one of the main consequences of spectral theorem of the spectral radius, which I'll mention as a theorem right now, right? A to the k goes to 0 as k goes to infinity if and only if rho of A is less than 1. Okay, so basically A to the k, meaning you are starting with the matrix A and you are taking powers, right? And this power is going to infinity, the power k goes to infinity, meaning you are taking larger and larger powers, right? As you keep taking larger and larger powers, right, you want the matrix to go to 0. Now this needs to be explained. What do you mean by matrix going to 0, right? For simplicity's sake, here let's assume I'm just saying entry wise, meaning that every entry, so remember this is a matrix, right? Okay, we are dealing with square matrices here because you cannot take the powers of rectangular matrices, right? You can only take the power of a square matrix. Okay, so when you take repeated powers, when you take larger and larger powers of a square matrix, then you are saying if I want all the entries of the resulting matrix to go to 0, right? Entry wise limit 0. Okay, if and only if the largest eigenvalue is 1. So this is very similar to the scalar result. A to the n goes to 0 if and only if absolute value of A less than 1, right? If A were a scalar, if A to the n has to go to 0 as n goes to infinity, right, then the absolute value of A has to be less than 1. So this result in essence very similar to that. Okay, a to the k goes to 0 if and only if rho of a less than 1, right? The proof is actually not beyond our reach. Let me just very quickly run through it, or maybe you can check it in the notes, right? Let me just do, so basically it's an if and only statement, so there are two parts to it. Let me just do one part, right? So a to the k goes to 0 implies rho of a less than 1. We have to do this one, and then rho of a less than 1 implies a to the k goes to 0. We have to do both of these. Okay. For this part, I'll leave this as an exercise because we already covered this a bit in the power method we did before. Okay. So the main idea is, suppose that, for this part we are saying if a to the k becomes smaller and smaller as k increases, then the spectral radius has to be less than 1, right? To prove that, you can just assume the converse. Suppose that the spectral radius is bigger than 1 or bigger than or equal to 1, right? Then simply by focusing in the direction of the eigenvector corresponding to the largest eigenvalue, I can see that a to the k does not go to 0, right? That's what gives you this part. So I'm leaving this as an exercise. Those of you have any doubts, you can ask me, right? The second part is what we can try. Okay, if the largest eigenvalue is less than 1, then a to the k goes to 0, right? For this, simply we can just take a leap of faith for now. Assume A is symmetric. Even though this result doesn't assume any symmetry, assume A is symmetric, then A is like VDV transpose, right? Right? Then what is A to the k, right? A to the k is V, D to the k V transpose, correct? Now D to the k here is the kth power of all the, D is a diagonal matrix, right? So what happens when you take the kth power of a diagonal matrix? You simply get the powers of the diagonal. So lambda 1 to the k, lambda 2 to the k, so on, lambda n to the k. This is what you will get, right? In this matrix D. Okay. Now we are saying that the spectral radius is less than 1, which means all these eigenvalues have absolute value less than 1. They are between minus 1 and 1. It's a symmetric matrix here. So eigenvalues are all real numbers between minus 1 and 1. Okay. So when you take the power of k, right, as k goes to infinity, all of these will go to 0. Okay. So this whole matrix in between will go to 0, meaning this whole thing will go to 0. But all the entries of a to the k will go to 0. Okay. That proves this part. Of course, I have only proved it when A is symmetric, right? Okay. When A is not symmetric also, you can give a proof. That is actually very similar, but for that we need Jordan. We need the Jordan form that I referred to earlier. Okay. So I'm going to skip it. Once we do Jordan form, we can actually revisit this and prove it even when A is not symmetric. Okay. So as I said, this is one of the key ideas where spectral radius comes in, right? So where do you use norms? So if I know that the norm of a matrix is less than 1, doesn't matter which norm it is, it could be the spectral norm, for example. If norm of a matrix is less than 1, then the spectral radius is definitely less than 1. Okay. So A doesn't even have to be symmetric here, right? Any matrix A, if its spectral norm is less than 1, then you know that its spectral radius is less than 1, and then you know that A to the k will go to 0 as k goes to 0. Okay. One consequence of this is this series, right? So when you can talk of something like this, I plus a square plus a cube plus so on, you can keep running this series. You can take large number of terms in this series. Okay, suppose you take large number of terms in this series, right? So basically you are looking at this summation, right? This is an infinite summation, so it's a series, right? Okay, so this sum runs, it's basically you can write it as summation of a to the k equal to 0 to infinity, right? So one can show, and we'll skip the proof here, using very similar ideas to the proof of this theorem over here. Very similar ideas. Can prove that this series actually converges to I minus A inverse if the spectral radius of A is less than 1. Okay, the spectral radius of A is less than 1, then this series over here is converged. So just like when you have this series, right, 1 plus x square plus so on, if you take this infinite series, we all know that this is converges to 1 over 1 minus x if x is between minus 1 and 1. Right? In fact, you can allow x to be complex also, so long as the absolute value of x is less than 1, then you get the convergence of this series, correct? Similarly, for matrices also you can talk of convergence, right? Here, for the sake of simplicity, I am simply talking of entry-wise convergence, right? So when you construct this matrix, every entry of this matrix converges to the corresponding entry of this matrix, I minus A inverse, okay? Now, this works only if the spectral radius of A is less than 1, okay? So this actually gives you a technique to invert a matrix, right? For example, suppose it turns out that A has a very small spectral radius, right? If A has very small spectral radius, okay, meaning that A to the K goes to 0 is very small, right? So here in this series, maybe I can approximate this series with just a few terms, so maybe I plus A square. Okay, I'll approximate this series with just 3 terms, I plus A square, right? Maybe if the spectral radius is really small, I can just approximate it with only 2 terms, I plus A, right? And then that will be an approximate inverse of I minus A, right? So I minus A inverse is approximately going to be equal to I plus A if A has very small spectral radius, okay? So that gives you huge computational savings if you already have some information about your matrix A. If you know that your matrix A has a very small norm, it's known in advance, then to invert I minus A inverse, I could simply approximate it with I plus A. Now this, remember, is just adding identity to all the diagonal entries of A, right? So it's just linear order n operations instead of order n cube that you would need to actually invert the matrix, okay? So this is called the Newman series. It's called the Newman series, and this summation converges provided the spectral radius of E is less than 1. And one way of ensuring the spectral radius is less than 1 is to ensure that the norm is less than 1. The spectral norm is less than 1. Okay. Stop this lecture.